you know, if these rules that we had talked about earlier um, just seem odd, we'll try to clear that up a little bit in these next few minutes and then get ready for some of the stuff on today's assignment. All right. So to look at the voltage loop rule and the current junction rule, I'm going to go and back and forth between two different things. The two different things, one of them is the notes that are posted in classwork. So classwork, click it. And then here's like the blank sheet version of that that has a spot where if you're the sort of person that would like to print it out and then write things in, because as you write things in, they kind of stick better. There you go. If you want the copy that has all the stuff in there, well, there you go. Teacher copy, direct current notes. So those two have the same spaces. This one, the spaces are filled in. So I'm going to open this one. One of the things that we're going to use, go back and forth on when we're looking at voltage loop rule, current junction rule, in Ohm's law. One of those things is this section of notes. And then the other of those things is this assignment from Tuesday, Ohm's law, loop rule, junction rule, that the practice assignment for that. There are some diagrams in there and some questions there that'll be helpful to kind of go back and forth. All right, I forgot. I need to click on the chat, so if somebody types things, I see it. I just clicked on chat. So one of the first things that I wanted to, well, here, you know what, we'll do a big lay of the land on this teacher note thing on these note copies. So no, we'll go back to this. There we go. So we've already discussed, it's been a little bit, but we've already discussed the ammeter and the symbol for an ammeter, and that amps are, it measures current, excuse me, which is measured in amps. We've talked about batteries that motivate the charges that are present to move. Bulbs convert the electrical energy to light energy, possibly light and thermal energy. Usually, if it's a filament type bulb, usually thermal and light. A circuit is just a path for charges to follow. A conductor is a material that charges flow through rather easily. Um, Conventional current is kind of an awkward thing, but in wired circuits, circuits with wires, as opposed to there are some liquid-based circuits. In wired circuits, it's really electrons that move one way, but we learned that after we had talked about, we learned about the atom, and we learned about the existence of electrons and how they're different from protons. We learned about that after we had already started talking about charges or current going the other direction. So crap. So what we can say is that if I give you $1, I lost $1, you gained $1. So we can say it's a +1 to you, which would be like conventional current, like a positive going that way. Or we can think of it as a -1 to me, I lost $1, right? Both of those descriptions describe the exact same event. It's just one way is describing the like a positive flow to you, you gained $1. Or we can talk about the negative flow to me, I lost $1. I am now more negative in terms of financial security than I was a bit ago. So that's the same sort of thing. The negative is the direction that electrons are traveling. The positive is the direction that some positive charge is traveling. We would try to avoid saying protons because it's not really protons, it's imaginary blah, 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 and that's that buggered confusion from before. But um, I, I don't want to spend too much time there. Current, moving charges. The basic thing for current is it's the number of charges per second past a spot. So current is measured in amps, coulombs per second, charges per second. That stuff we did already. The current junction rule, and you know what, I'm going to hold off on that. We'll do this in a minute. Because the first thing on the list was the loop rule. And so I'll try to just stick with that. So we had talked about electric potential. That's also often called voltage. So I'm going to slow down a second, take a breath. We did a bunch of review, but now here we're starting to hit one of those new items or an item that's involved in this new thing. So electric potential is the energy per charge that the battery provides to all charges in that circuit. So the battery provides energy to all charges in that circuit. And that energy per charge is electric potential or voltage. It's not the total energy for all charges, but it's the energy per charge. If we're playing dodgeball and we talk about, maybe like a pitching machine might be better, right? So a pitching machine, like, you can put a baseball in a pitching machine and the wheels spin and there she goes, right? Um, if we have one pitching machine and we have it set to 100 miles an hour, you better be good because 100 miles an hour is coming at you. But if we have that one pitching machine set to throw it at 100 miles per hour, each ball is coming at you with a certain amount of energy, right? Not speed, but we'll try to say energy for that baseball. Now we have another pitching machine set up that's set up to identical stuff to give that ball the same amount of energy coming at you, right? So now you have two baseballs coming at you with the same amount of energy. So we can talk about the energy per baseball. If we have a third, set it to the same power settings, all three baseballs coming at you with the same amount of energy. The machine is giving every one of those baseballs the same amount of energy. It's not the voltage or electric potential, it's not the total energy, it's the energy given per charge. Or if we just have the one pitching machine standing there and we send one baseball through, then we send another baseball through, then another baseball and another baseball and another baseball, right? Each baseball gets the same amount of energy as it goes through. So the total energy would be like the sum of all of those baseball energies. But the voltage or electric potential is like the energy per charge. Now, when we look at that, that is going to lead us into, where did the loop rule go? Current junction rule? Conventional current? Oh, when I made edits, did I get rid of the dang current loop rule? I might have. I have it back. Oh my God, I have it here, but I don't have it on the front. Good Lord. So the current loop rule, or pardon me, the voltage loop rule. The voltage loop rule says that as we go around a circuit, if the battery gives each charge 4 volts, then as the charges go through the items in that loop, the charge loses that energy. So it's like the charge gains 4 volts here, loses something here, loses something here, loses something here, and it's back to 0 volts. Plus 4 volts, minus something else, minus something else, and now it's back to 0. So we can talk about the loop rule as saying, hey, the battery, whoopsies, the battery gives us this energy. The battery gives us a voltage, a potential. The first resistor takes some, the second resistor takes some, and I guess if we were linking it to this, the third resistor would also take some. So it'd be plus from the battery, minus from resistor 1, minus from resistor 2, and then with this one, there'd be an additional loss in electric potential or voltage drop for resistor 3. If we add all those together, the positive from the battery, the energy per charge the battery gives, and then the energy per charge that the first resistor takes, the energy per charge the second resistor takes, the energy per charge the third resistor takes. If we add all that together, we end up with 0. I think here is kind of a nice way to take a look at it. So if we look at this, we'd be saying that the battery gives us 9 volts, and I'm just looking at the blue loop. Yeah, the loop rule. There are 2 loops. There's the blue loop and the orange loop. In the blue loop, following one charge, not all charges, just trying to think about one charge. One charge would gain 9 volts going through the battery. And so if the charge starts off with 0 volts, 0 volts, now at this location, that charge has 9 volts. At this location, 9 volts, 9 volts, 9 volts, 9 volts. And I'm going to follow the blue path. So if the charge, any charge that's here is at 9 volts, any charge that here is at 9 volts, any charge here is at 9 volts. And then as it goes through this light bulb and that filament, the 9 volts of potential, or the 9 joules per energy per coulomb of charge, the voltage, the energy per charge, is used by the bulb. It becomes warm and it gives off heat and light. And so now here it's acts as 0. 0 volt, 0 volt, 0 volt, 0 volts. So it's like +9 from the battery, -9 from this bulb, and that charge at all charges at this location, but if I'm tracing just one charge, the charge as it goes through here is now at 0 volts of electric potential back there. If we follow the orange path, the exact same thing, the exact same analysis still works. I'm not looking at that same charge, I'm now looking at a different charge. So if I'm looking at a different charge, taking a different trip, a different path, that charge here is at 0 volts. And as it goes through the battery, that charge gains 9 volts. It's at 9 volts, 9 volts, 9 volts, 9 volts. All charges here are at 9 volts. And before we followed a charge that took that blue path, now if we take a charge that takes this orange path, this charge is now over here. Well, it's still at 9 volts. It hasn't gone through anything that's taken energy from it or used energy from that charge. So the charges are still at 9 volts of potential. Every charge at this location has 9 volts of electric potential. And then when this charge goes through this bulb is different from this one, 25 ohm, 40 ohm. You can see that they're even at different brightnesses, right? But still, even though they're different bulbs, different brightnesses, when it goes through here, this charge that goes through here uses up, or I shouldn't say uses up, that charge loses the 9 volts of potential that it had, and those joules per coulomb of energy go to making this bulb warm and giving off light. Since this bulb is a different type from this one, the temperature change would be a little bit different and the light would be a different brightness, but that's only because this bulb is made differently. It's made differently, so that same amount of voltage produces a different temperature and different light, but it still uses 9 volts. And now that charge is at 0 volts of potential. In fact, any charge here is at 0 volts of potential as it goes all the way back to the battery. So that's the voltage loop rule, is saying that plus voltage from the battery minus voltage for whatever is using energy, and then we should add to 0. So if I take this plus the negative from here, we should be at 0. This plus the negative from here is 0. If we take the orange path, this plus the negative from here, we're back to 0. And that doesn't matter if there's 1 bulb, 2 bulbs, 6 bulbs. It doesn't matter if there's 1 path, 2 paths, 6 paths. No matter what, that is how things go. So that's that voltage loop rule. And that's what's described on this part here, where we can say that as we go through these things, we end up being back at 0. All right. And then current and the current junction rule. So that's the next part. Let's see if we can make sense of that. So the current junction rule is if we're counting charges as they go through, there's this thing that we cannot create or destroy charges. The universe does what it wants. We cannot create charges. We cannot destroy charges. So if we have a circuit, and we can go back to one like this, we'll find, so if we have a circuit here and we have a bunch of charges flowing through this circuit, if we have, let's say, 10 charges per second going through this region, so that means 10 charges per second enter this junction. This little spot here is like a junction. Charges can either go down or they can go over. Yeah. So if 10 charges per second enter this junction, then 10 charges per second total need to leave that junction. So maybe 6 go down per second and 4 go to the right per second. It could be 5 and 5, it could be 8 and 2, but the idea is that the total in must equal the total out, has to. Because if it doesn't, then that means that we've destroyed charges or we've made charges disappear or something. And that just doesn't happen in this setting. So that's the idea of this conservation of charge being applied to junctions. So I hope that makes a bit of sense. So the equation for that is like total current in equals total current out. And then here's voltage loop rule, word-based deal for voltage loop rule. And now Ohm's law. So that's the one that we got from our Pivot Interactives lab that we did last week. I think that one was last week. My memory, I don't know. It could have been Monday, Tuesday this week. So Ohm's law is that the current and the electric potential are proportional to each other. So if we double the voltage or the potential difference across like a light bulb, if we double the oomph of the battery so that that bulb uses twice as much voltage, then the current should double. If I double the voltage, the current should double. And we end up with this equation. The current, I is current, equals 1 over the resistance times the potential difference. I have another version of this that's, I think, worded more clearly. I thought 2020, 2021. I don't know what I did with that other one. I'll try to see if I can find that and replace that in here today yet. But so current is proportional to the potential difference. If the potential difference across a resistor or a bulb doubles, then the current doubles. If the potential difference across a bulb or a motor, if that reduces by half, well, then the current would be reduced by half. So current and potential difference are proportional. Double one, the other must be doubled also. Half one, the other must be half also. Triple one, the other must be tripled also. Resistance is not that way. And it kind of, I mean, this is another thing, another relationship that kind of makes sense. I mean, it's based off of data, so it's not guessed at. It's based off of data. So if the resistance increases, the current, the amount of moving charges per second should decrease. I mean, that kind of makes sense, right? If we think of the current as like people walking down a hall, well, we can't obliterate people from existence. We can't turn them into not even dust, but just energy. That doesn't happen. So no matter what, as people are walking down a hall, you count those people, they're going through. That's that, right? If we put them all on a slide, they're all going to be going through. So the slide, like the difference in height can be like our potential difference, like the voltage used to make people go down the slide. So if we make the slide just a little steep, our current would be kind of small. If we make the slide steeper still, so we have a bigger change in potential, yeah, then the people would be going faster and faster. If we add like bumps to the path, or if we add little obstacles, the things that people as they're going down the slide they bump into, that'd be a terrible slide. But those obstacles would be like the resistance in the circuit. And so those, if there's more obstacles, the more resistance there is, the slower or the smaller the current would be. So if the resistance goes up, the current goes down. If the resistance goes down, then the current should go up. The name for resistance makes some sense. All right, and so Ohm's law is the name for this relationship. I sometimes say, hey, I don't worry too much about names for things. I don't generally worry about names for things. Newton's first law, Newton's second law, Newton's third law. We can talk about what they are discussing. But with Ohm's law, it's kind of, I'll often refer to it as Ohm's law, because otherwise what am I going to say? The relationship between current, resistance, voltage? So when I say Ohm's law, this is the equation, this is the relationship that I'm talking about. We did get it experimentally in our Pivot Interactives lab. There are other actual labs that we can do to get this experimentally, but this is Ohm's law that we're using here.